beg your pardon, guys, we have some.
Friends of the game. Carrying it and then knock it out of my hands. I can't spray. I did it and then knock it out of my hands. I could spray.
I'm not going to listen to this because I don't want to get past.
Okay. So as promised, I have your exams here. I did not total them at the top. Well, I guess I did. Okay.
This is digital. This is digital.
Now backwards, there's that one. There's that one. Jesse. That one. Blake. Okay. So, I'll entertain questions about those. We'll talk about those at the end. So as not to rob you of your learning opportunity. Does anybody have any questions? Systematic questions? Any questions? Process questions? I'll dig in. Okay. And I think I told you the average standard deviation that was in the email I sent out. Right, everybody see the email?
Oh, I forgot. What was that?
81.5%. All right, so today we're going to spend, well, today and Wednesday, we're going to talk about shear. So we've covered all of the ways, all of the basic normal deformations. So we have normal load, axial load, transverse load, axial rotation or torsion, and transverse rotation or bending. Those are the four things we've talked about. Right? In fact, transverse load was basically what all statics was about. It was only the axial load that we started to get into stuff we can't talk about in statics because we actually have material deformation involved. So today we're going to talk about shear. So unlike all those things we've already discussed, shear is not easily defined in terms of the shear distribution across the cross section. So if you look at the canned ham that's on the screen there, we have a distribution of shear stress across that face. That's a cross section of an elongated beam, delta dxy. And there's a distribution of shear across that face. And it's going to be hard, it's a little more challenging for the shear than it was for the earlier analysis of normal stress across the front of that face. Because the issues are that shear, right, we know what shear is, right? So if I have a specimen and there's some transverse load applied, it creates a shear, right? So that shear is sort of creates a moment, right? Shear V will create a moment. The moment creates a varying axial force, as we've seen before. Right? Varying axial force. In other words, the component of force into the face, as we've drawn it on the canned ham, right, varies as we move up or down. Where is the component of force into the ham? 0. Where is the component of force into the face? 0. What little element of that face experiences 0 normal force due to bending? The neutral axis, right? NA. That's what the N and A stand for. Right? The neutral axis is the point where you don't have any force. If I'm bending it upward, the top is going to experience what? Compression, and the bottom, tension, right? So if I shear, if I take one end of the thing and push up on it, then I'm creating a moment, a bending moment, in addition to a shear. Right? The bending moment creates, or the shear creates a bending moment as well as the shear. That moment that it creates these varying axial forces, different stresses along the height. And then each of those axial forces, in turn, create a local shear. If I bend on this, if I push on this one more than I push on this one, then I'm creating a shear. Right? So if you remember when we did if I did a sort of a side view of this specimen here, right? And I'm squeezing it up like this, there's a big force pushing up here. Here's my neutral axis. And maybe it's about a third. Okay, so here's my neutral axis. There's a big force there, there's zero force here, right? And there's less and less force as I go down. Right, you remember that? Right? So I'm creating a shear if I'm on this little element here because the top's being pushed more than the bottom. I'm creating a shear on that little element. You see that? Qualitatively, okay? So the varying force of stress, the varying force, creates a shear. So it's a complicated solution. But what we're going to do is we're going to take, oh, and one more thing. If I take a little block and I want to know the shear stress, tau, acting on that block, right, due to this applied, right, I'm creating a tau here when I apply that force, right, because there's a reaction force down here in the downward direction. Right, so I'm creating a shear on any element within there. But also keep in mind, from what we talked about before, that this is tau y, this is tau x. The tau x has to equal tau y because that moment doesn't rotate. Remember we talked about that back when we introduced shear stress. So the shear stress on this y plane is equal to the shear stress on the x plane. So what we're going to do is, because of all this variety here that gives us a little bit of confusion, we're actually not going to solve for tau y, we're going to solve for tau x. And then, because we know that tau x has to equal tau y, we solve for tau y. That make sense to everybody? Okay. Okay, so therefore, tau sub x is equal to tau sub y. All right. So let's consider this drawing. Now, I've drawn the top half, the compressive half, but somebody over here said it was tensile on the bottom, right? So there's a stress on the bottom that is tensile, right? And given the fact that the bottom is fatter, if you look in the third dimension, into the dimension into the plane, T is a bigger value for the bottom than it is for the top. That's how the sum of these forces and the sum of these forces balance one another. Right, so we'll call this whole force on this side dF prime, the total force for this little increment dx. So dF prime is the total force pushing back from the right-hand side. And dF prime is equal to 0. Because the compressive stress is exactly canceled out by the tensile stress and through the neutral axis. That's how we did that whole analysis for bending, right? There is also a reaction force on this side because there is a moment, on this side m, there's a moment on this side that is m plus dm. Right, so on the left side I've got a moment. On the right side I have a moment. Which one of those is going to be larger? Even though I said plus dm, dm can be negative. Which of those two is going to be larger for this configuration, this loading configuration? M or M plus DM could be bigger. Huh?
M plus DM, right?
Well, that's what I'm asking. Shall I take a vote? Which is bigger, the moment on this side or the moment on that side? This is a slice out of the center, right? I'm just taking a slice out of the center of this bar, this beam.
M plus DM. It's farther away.
Got 2 votes for M plus DM.
3 votes.
3 votes. Going with M plus DM? You have no opinion? Okay. So how do I get M from, how would I calculate M if I was actually trying to calculate M? What did we just do on this test?
You can sum the forces of the triangle.
Or, yeah, we don't know what that is. I'm just saying, this is my condition. How would I get to solving for M? You just did it on the test. Well, most of you just did it. I do a shear moment diagram, right? The moment here, M, is the integral of v dx as I move along that thing. Right? It's the area under the Vx curve, right? Well, the Vx curve, if you think about it, is this, right? With some V, whatever's applied. And so I start out at F, and it's that value all the way across. So as I go from left to right, I'm increasing my moment. So V plus dm is bigger than M. Or M plus dm, rather, is bigger than M. Right? I'm increasing the moment as I move further along. Okay. So that means that the force, the total force on this side, is different. I mean, at any point in here is smaller than what's over there. Any element of force over here is different than what's over there. But if I add all this up, it also cancels out. So I have 0 net force on this side, 0 net force on that side. Right? Because every one of these compressive forces is balanced by a tensile force down here. Every one of these compressive forces is balanced by a tensile force down here. The total on the left is 0, the total on the right is 0, so the total force is 0. And everything's in equilibrium and everybody's hunky-dory. Everybody's happy. Right? But I'm going to do another section. Instead of just sectioning a slice this way, I'm now going to take that same slice and I'm going to section the top piece, A prime. Top half of the can, or top third of the can here. You see that? So I'm going to take, instead of just looking at the whole thing, neutral axis here, I'm only going to look at this piece. Just the top third. So I'm only looking at the top part of the hand. I should have handed that test back at the end of the class. There you go. All right. So now, is the total force going to be 0 in this case? The total force in the top third of the cantilever? No. Because now, my df prime piece over here on the right is going to be bigger than that on the left. So on this top section of the material, there must be an additional force because the top section of the material is not moving. Right? That top section is not translating through space. So there must be an additional shear stress, represented by shear tau, shear stress, on that bottom face to make it all balance out. Listen right here. There has to be a shear stress on this top piece in order for this force diagram to balance out. So if I do the sum of the forces, am I ready to do that yet? Yeah, we're good. Okay. So now if I do the sum of the forces, oops. In the x direction. what do I have? Well, I have the integral over a prime, just that top section of the canned ham, a sigma dA prime. And that's what's on the left-hand side here. It's a positive force. Minus the integral over a prime of sigma prime dA prime, which gives me the force pushing back, plus the shear stress times the area on which the shear stress acts. What's the area on which the shear stress acts in this case? Look at the picture, tell me what the area on which the shear stress is acting. dxt. But I'll make it TDX because just it's a lot easier to put the dx. Okay. Right, so dx is this width, t is the thickness, so TDX is the area on which that stress acts. So I multiply that stress times the area on which it acts, that gives me the force. Right, does that make sense? Okay. But now, going back to over here, right, the shear creates a moment, with moment creates a stress, the stress creates a shear, right? Now I'm going to go back and represent this stress here, the shear stresses, in terms of the moment that created them. How do I relate shear stress, or I mean normal stress, and the moment? Remember from the equations that we just used, say,
mx over I.
X over I.
I something. I, y. I, x.
Y.
Z.
It's actually my over I. Right? The stress gets bigger the further we get from the neutral axis. That's the y position. Right? Okay. So stress is my over I. So I'll take this integral over area prime of my over I dA prime minus this, the integral over a prime of now m plus dm over I times y dA prime plus still the tau t dx. Right? The only difference between these two is the dm term. So the sum of the forces, the total force in the x direction, is just equal to the integral over a prime of dm y dA prime plus tau t dx. Oh, sorry, forgot my over I. Okay. dm does not vary with a. Right, the moment the dm is applied universally over the whole cross section. So I can pull it out of the integral. dm over I times integral over a prime of y dA prime plus tau t dx. And what's the sum of the forces? 0. So, I'm sorry, that's a minus sign. It's a minus sign. I'm trying to the minus sign. So, tau t dx is equal to dm over I times integral over a prime of y dA prime divided through by the dx and the t. Tau is equal to dm over dx times 1 over it times integral over a prime of y dA prime. And what's dm over dx? dm dx? Shear, V. So we're almost there. Yeah,
How do we know dm over dx is shear?
because remember that we did the whole thing, that's the shear and moment diagrams,
Oh, right.
right? So if shear is the derivative of moment, or moment is the integral of shear. Okay. So, we've almost got it. We just had this extra thing on here. It's a little different than what we've had. What does that look like? That y dA prime, the integral for a prime of y dA prime. What kind of a function does that look like? We've seen a similar function before, just in other primes. What was that for?
Isn't that just the centroid?
Is the numerator?
Yeah, we used that when we found the centroid, right? It's the numerator of the centroid, right? So it's the, so this piece here is equal to the centroid times the area. So, but it's the centroid of just the top third of the cantan. It's the centroid of area A prime. It is not the centroid of the cross section. We see that? So you see here the y prime bar in the graph points to the centroid of just the top third of the cantan. Yeah.
And that's just because we did integral of y with respect to the derivative of a prime. If we would have just used a, would it be the whole
If it had been A, then yes, it would have been. But we're summing the forces. If we did A, the sum, it becomes moot, right? Because when we're back here with A, we know df prime is 0 and df is 0 and it all balances out. So it's only when we limit ourselves to just this top section.
Why are we limiting ourselves to the top third?
I just picked a third. I
Okay.
mean, that's just, it's not even a third, it just looks like it's maybe a third.
Okay, so just the top.
I'm just picking some random section, right? But the key here is we're solving for the stress, the shear stress at that interface. Right? So the shear stress that we're solving for, this tau, is your shear stress at that particular height, y prime. So if I ask for the shear stress 2 centimeters above the neutral axis, then I cut it off and I say, okay, I've got the shape 2 centimeters above the neutral axis. I got V, that's easy, that's a global parameter. I and T, I is still I of the whole cross-section, moment of inertia of the whole cross-section. But then I pull in this y bar prime times A prime. The area above 2 centimeters and the centroid of the region above 2 centimeters. Okay, so this part corresponds to just the part that I cut off, the part that's above the level where I want to find the shear stress. This corresponds to the whole thing. So you get two different sort of regions that you're working with. The I is the moment of inertia of the whole cross-section. This y prime bar times A prime is just the centroid and area of the portion above the location where you want to find the shear stress. And we call that Q. So that in the end, the expression for shear stress is QV over IT.
Can you describe Q? I know you just did, but
Do it again. Okay.
please.
So Q is the product. Q is a characteristic of the portion of the cross-section above the point where I'm trying to measure the shear stress. So if I want the shear stress distribution, I have to calculate the shear stress here using one Q. I calculate the shear stress at this point using a different Q. Q changes as I move to a different height on the cross-section. V, I, and T are the same for the whole cross-section. So Q represents the distribution of that shear stress as I move through the cross-section. that make sense? Okay. And it is the product of the centroid of that remaining area times the area. Okay.
And so this is the tau and like the x-axis at a chosen point.
This is tau at the x-axis at a chosen height, y prime, above the neutral axis.
So then you said that the tau in the x direction is the same as the tau in the y direction, but where is that tau in the y direction that this tau is equal to?
So it would be pushing down, and or you know, it's the piece that's sticking on the either side. So if I take this thing out, there's a piece of shear stress happening here.
Okay.
So there's a shear stress happening here, and at that same surface, there's a shear stress happening here.
Oh, so it's just still at that given, or that chosen spot.
Yeah, right. So this tau, right, this is dxy, and I would have a piece that's dyy,
Okay.
right? So there'd be some finite, and that little chunk
That little spot has
is
the-
experiencing a stress, and you know, shear stress here.
Gotcha.
Okay. And this is the sort of the shape of the overall diagram. Okay. All right. Is that? Anybody else have any questions? So Q is the only thing that varies with position. Q is what represents, what governs the distribution of the shear stress. And clearly Q is not going to be a linear function most of the time, right? Unless this is a linear function, which it might be if I had a rectangular cross-section. If I have a rectangular beam, right, then this falls off linearly with y. This falls off linearly with y. So Q is actually going to fall off quadratically. If I have some other more complex structure, it's going to fall off some funky way, right? I don't have a, there's not a nice mathematical easy representation for Q because it varies depending on the cross-section. And the more complicated the cross-section, the bigger the variation in Q.
So if you go below the neutral axis, is it just negative?
It would just be shearing in the other direction. Remember, we said anything that causes causes clockwise rotation in the y direction here is a positive shear. So it would just be pushing the other way on the bottom right.
Okay.
So where's the maximum shear going to occur?
When Q is right?
Okay. When is Q max?
Closest to the neutral axis.
Right, at the neutral axis. The maximum shear occurs at the neutral axis. So you can see that here, because Q's got to be big, then A's got to be big. The biggest A prime you can get is the whole top half of the thing. Right? Or you can see it over here and recognize that the difference in these forces just gets bigger and bigger and bigger. The absolute difference in the forces, therefore the absolute size of the shear stress, increases as I get down to the neutral axis. Once I get past the neutral axis, then I start to decrease because the bottom half, the forces in the bottom half begin to compensate for that difference. That make sense? So the biggest shear occurs at the neutral axis. T is the thickness, and you gotta keep track too. T is the thickness of the beam in the z direction essentially. T is the z dimension of the beam in this picture. Y is this direction, X is this direction, Z is that direction. Okay, so T is the Z dimension. And again, as I said before, the main thing to keep in mind is that these are global parameters. DI and T are for the whole cross section. Q is the only one that varies with the little pieces. Okay, a couple of things built into this. We've assumed that tau, the shear stress, is uniform across T. We assumed that tau was the same. So all we did was took tau, multiplied by T dx. Right, so we assumed that the shear stress as I move in the z direction was constant, and it turns out it's not. The shear stress is slightly higher at the surface than it is in the center. But for what we're doing, that approximation will hold. And the thicker the part, the wider T becomes, particularly in relationship to the total height of the beam, the more that it varies with the depth. So in other words, if I've got a beam that's really skinny, right? And I zoom in on the shear stress distribution there. The shear stress distribution might only curve a little bit. Okay, you see what I'm saying? This is just a reference line. So the shear stress amplitude is slightly more at the sides than it is at the center. Okay, but if I take a beam that's just the opposite dimension, right, and then plotted shear stress across there, I could get a really big distribution of shear stress. Okay, so the shear stress across the z dimension can vary significantly if that member is wider than it is high. But as long as the height is roughly 2 times the width, we don't have to really worry about it. Okay. So, also, this whole analysis only works if the shear stress, if the line that we're calculating shear stress for is perpendicular to the surface. Okay, my computer's taking it back. So, in this case, you can see it's not perpendicular to the surface, right? So the shear stress, just to do the boundary conditions of the edge of the surface, the shear stress at this location has to be, because of the boundary conditions of the edge, it cannot be perpendicular, it cannot be vertical in this case. It cannot be perpendicular to the TDX plane. Because if it were perpendicular to the TDX plane, you'd have no material supporting it on top and you'd have extra material on the bottom. You see what I'm saying? So when you have a situation where the plane on which you're analyzing the shear stress is not perpendicular to the edge surface, then this analysis falls apart. But the analysis works as long as you have perpendicular sides. So think about it, most beams, like an I-beam, right? An I-beam, you're going to stress it orthogonally. And so the sides will be perpendicular to the direction of the shear stress you're trying to find.
So this analysis doesn't work in that picture, is what you're saying?
So this analysis doesn't work at the edge of that picture, yeah.
Mm-hmm.
Right. Because the direction of the shear stress can't be perpendicular to the plane. Okay.
But it does work if you take a section out of the middle,
But it does work if you, yeah, on the neutral axis it does. in
which
this
is what
picture.
we're doing here, right?
Well, I mean, this is just, yeah, right. Okay. So, again, there's a lot of simplifications that we've got involved in getting us to where we are here, but because of this interaction, because of the fact that these are so intertwined, it just requires a lot more detailed elastic theory to solve. And we're not going to get into all that at this point. It's more of a graduate level kind of solution. Okay, so we'll work with the simplification, with the assumptions that we have to work with. Unfortunately, for most of the samples we'll have to deal with, that's okay. So for instance, that I-beam there. You notice the I-beam, the center web is long, h is much greater than t, and so we're good on that standpoint for the uniform distribution of the shear stress. And the sides are perpendicular to the cross-section, so we meet that criterion as well. So for the I-beam, we can go ahead, and for the square beam below it, both of those work. Okay, so does anybody have any questions before we jump on to the problems? Questions about what we're covering today, not about the exam sitting in front of you. You turned it over, but you still couldn't help yourself.
So,
Okay. Anybody have any questions before we jump in? Okay, then let us jump. Okay. If the wide flange beam Flange is the top, the web is the middle. I think I was trying to come up with those words sometime last week or the week before, and I couldn't remember web and flange.
Which one's the middle?
The vertical piece is the web,
Like
Web.
a spider?
yeah, like a spider, of the I-beam, and then the two cross pieces are the flanges. So we have a wide flange beam. Flanges are wide. Subjected to a shear of 20 kilonewtons, determine the maximum shear stress in the beam. Okay, so we're going to find the maximum shear stress in that beam. What are we going to do? First of all, where's the maximum shear stress going to be?
And neutral.
Which is where on this diagram? Right, in the very center. So we know if we're trying to find the maximum shear stresses, which is what we really care about, right? That's what a lot of this other stuff here, a lot of these, you've assumed things, and we don't have to worry about so much because most of the time, we're only interested in the maximum shear stress. We don't care if there's a smaller shear stress up here because the thing's going to yield because of the maximum shear stress. So it's always, I won't say always, most of the time we're looking for the maximum shear stress. So we can deal with some constraints because as long as those constraints don't apply at the location of the neutral axis. Okay, so it's in the middle. We know it's going to be in the middle. How are we going to find the maximum shear stress in the middle? What do we want to do first?
Free body diagram of the face.
Free body diagram of the face.
So we have a shear force.
Nobody? Fighting line like fight song.
The what? Fight zone?
We're loyal to you, Illinois. School song, I guess, not really fight song necessarily. We're loyal to you, Illinois. Anybody from Illinois here? All Indiana
Is that
people
loyal?
from Illinois?
I didn't know that one. I just had an I love line on one.
Yeah, okay. Well, anyway. So, I was in marching band, so we had to play at the high school, we had to play.
Were you a twirler?
Okay, Colin's gonna walk us through the rest of this one. All right, Colin, what do we do next?
Well, we need to.
Looking for maximum shear stress.
Do we need to find the place where the moment is greatest from point A or from?
Tell you what, why don't you first give me a, let's finish the free body diagram first. Okay?
Okay,
So the
sure.
main thing with the free body diagram is just dimensions. Right, there's no extra forces, you're just doing the face, so we don't have really forces to worry about. We just want to make sure we got the dimensions right. So we have this dimension is 0.2 meters. We have this dimension, 0.02 meters. We have this dimension, which is 0.3 meters. And it's symmetrical, so the bottom's the same. Now, what is it we're trying to find?
Maximum shear stress in the beam.
So what expression might I use to start with? You might notice that I strategically did not erase the entire board.
So maybe we use the expression at the very bottom, QV over IT.
So tau equals QV over IT. Are we trying to find tau, or are we trying to find a specific tau?
I think we're just trying to find tau, right?
Actually, what's it say? Determine
The max.
the maximum shear stress.
So tau by itself isn't just max.
Tau is a distribution of shear stress,
Oh,
right? So we want to find tau max. What variable on the right-hand side is varying that that would be maximized?
Q.
Q, right? Q is the one that controls the distribution. So we're going to want to find Q max. And so tau max equals Q max times V over IT. V is fixed for the whole cross section. I is fixed for the whole cross section. T is fixed for a particular location, right? And T thickness along that line. For the location of maximum, once we find the maximum Q, the T is going to be fixed. So
So
find tau max, I gotta find Q max.
So Q max, wouldn't that just be if we take the center of the entire beam? And the area of the entire beam?
So it would not be, because if you remember, I can see it, can you see it anymore? You can't see the shape up here anymore. Okay. As we talked about before, once we get below the neutral axis, the forces start to compensate, right?
Okay. So we just take 1/2.
So we need to find the value at the neutral axis. Right? We always know that tau max occurs at the neutral axis. Yes.
So you would take the area above the neutral axis, and then the centroid though, isn't the centroid prime, y bar prime with respect to the center line?
Right. So we just said. The area above the neutral axis
Yeah.
times the centroid height of that area above the neutral axis.
Mhm.
So really, the thing we want to describe here is twofold. We have to have this to get I. And we have to have this whole thing to be able to find I. But then for Q, we're interested in just that piece. Right?
Which would be the area directly above the
Neutral axis, right? So Q is going to be based on this A prime, this whole thing right here. And then we have to find, somewhere in here presumably, the position Y bar prime, the centroid of just the top half. So we have to find the moment of inertia of the whole thing, and the centroid of the top half, the area of the top half, and then the rest of it falls out.
What's T? Isn't that the thickness like into,
So T would be,
or is it thickness across?
so coming back to well here, if we go back to this thing, you can see the T is in the Z direction, right? The face is the YZ plane. This face is the YZ plane. X is the length of the beam.
Yes, okay.
So-
I see it.
This is T,
Gotcha.
okay? All right, so let's start calculating some stuff. We've got 3 minutes. Let's first take the pieces for the whole thing. What's I? How many do we calculate I
I for the whole
for the whole thing?
It's gonna be 1/12 times 2 times 340 cubed minus 1.
Let's work in SI units. What do you say?
Oh, sorry. 1/12 times 0.2 times 0.34
minus.
Okay, let's talk about what that is, right? So what are you doing there?
So I'm taking the moment of inertia about the whole thing, and then we subtract the two inside. There it is.
Okay, so you're taking this whole thing and subtracting off the two sides. Everybody see that? The other option is to do each of the three pieces
Yeah, well.
and add them up. Okay, he's doing the whole thing. So we've got the 0.2, yeah?
Sorry, question about doing the three pieces. If we did all the three pieces, would we have to use a parallel axis theorem?
Yes.
Okay.
Like you would have to use the parallel axis theorem because this piece, you have to translate, in the center, it's a moment of inertia, or it's, yeah, well, yes, presumably, because you probably don't know offhand the rotation about this.
Yeah.
Okay, that minus,
It's gonna be 2/12 times. 90.09.
which is the width of one of these sections,
Yeah.
times 0.3 cubed. And 0.2501 times 10 to the minus third meters to the fourth is what I is. Okay, so that's I. Now we're going to find Q.
Q is 0.02 times 0.2 plus 0.15 times 0.02.
0.15? Okay, yeah. Okay. That's the total area. What else is in Q? Yeah, you gotta find y prime bar, or y bar prime.
Centroid.
What's that?
Just find the centroid.
Oh. So you have to find the centroid of this T.
0.17, I think, times 0.17.
Where are you, 0.17? I'm not sure where you.
So I just counted from the bottom and went to the middle of the beat. Started at the bottom.
So each of these has a centroid, right? So,
Oh.
right, we're gonna get y bar prime, right?
Yeah.
So we have to sum all of the centroids.
Yeah.
So this is the area, what's its centroid's position?
It's gonna be 0.
Not quite.
Well, plus the, let's see what's in this section. Do we just add the centroids?
Yeah, because the centroid, if you remember, the way we found the centroid was equal to the sum of the y times a, the centroids of each individual piece, divided by the total area. Well, this area is over here, so we just have to sum the other pieces. Remember that? Okay. So 0.16, right, because this one is 0.15 plus 0.01 plus 0.02 times 0.15 times 0.075. The height of this centroid for this piece.
For just a half of that,
For the half of the width, right? So fortunately, we don't actually have to find y bar prime. If we wanted to do it, we'd have to divide through by the total area to find where y bar prime was. Well, we've got Q, let me see what Q is. Q is there for 0.865 times 10 to the minus 3 meters cubed. And then plugging back in the T, the thickness of 0.02, and the V of 20 kilonewtons, we get the tau is equal to 3.459 times 10 to the 6th Pascal. or 3.459 megapascal. Okay? Good. So hopefully that helps. If you have any questions about the exam, let me know. I'll,
Do you need them back?
I think I already made copies. I think you're okay. You do know that sharing exams with other students is,
That's a big no-no.
So no.
as long as we're on that same page, then
Is selling a no-no? Just kidding, it's a joke.
sharing's the problem, but something's all right.
I think if you have to worry about anyone, you have to worry about Blake, considering he has the illegal book.
Yeah, good point. I didn't get a chance to, hold on, so that's like I tell myself, hold on.
Don't want to get it on camera.